Hello and welcome. Hopefully this is running properly. Let me check this. And assuming we're good, we just had some bad timing because a squirrel ran by right before the stream started. There's a chance we'll get some more squirrels, so perhaps if we take an intermission during our stream, I will grab some extra nuts for the squirrel, although it's already fond of the birdseed that's scattered all around. Welcome back to the combo classroom around here, where we have another Monday live stream, which this month I'm doing at 5 p.m. Pacific time on Mondays, in addition to whatever random other streams I do each week. We also did just release, or I just released, a new combo class episode on the combo class channel. So make sure that after this stream, if you haven't seen that, you tune into that, which is linked in the description. It is about a cool numeral base that some computers use instead of binary. But today, on this Domotro channel, I don't want to spoil too much of that episode because I think many people won't have had the chance to watch it yet. We're going to cover other things, and although our streams are pretty casual, I decided a good structure for these streams will often be to begin with a few welcomes, then get into a mathematical or scientific topic or two, and have those be the beginning portion of our stream. Then sometimes take a little intermission if needed, and then do a longer, chiller, chat answering, storytelling, question responding mode of the stream then. So feel free to leave questions. I may take some breaks in the earlier portion, but I will especially respond to some of your stuff in the second half. For the beginning, though, I do want to mention a scientific item I have here that I think we should start using right now, because from the box it says warms up in under 1 hour, implying it could take up to an hour or up to under an hour, which it's vague language. Under an hour does imply it is, a good little chunk under an hour, but by the technical logic behind it, it could be 59 minutes and 59 seconds it takes to warm up. So we might as well plug it in now. Now, what do I have? It is another cool science device that, once again, I'm not sponsored by. It was sent by George Carozzi, who's actually here in the chat, a awesome combo lord who has sent some cool science stuff, such as this one that I also have here. The Galton board, which demonstrates how bouncing off things randomly can generate normal distributions. And the new thing that I received is a lava lamp-ish thing, but I'm not sure what material's in normal lava lamps. I don't think it's this necessarily. This I've only heard of once or twice, but I remember it seeming very cool. It's called Ferrofluid, so it's a lava lamp that's going to have this other magnetic metal in it. And I did pull up, since I am not an expert in ferrofluid, the Wikipedia article right here. But I think to begin, before I get too sidetracked, we should look at this ferrofluid thing and see how to plug it in case it does take up to an hour to show its full potential. Because, these streams, you never know how long they'll be, but they almost always are more than an hour. Now, this is cool. They have some small magnetic rocks in here. You see, with the ferrofluid, one thing I do know about it is that it's magnetic in a way where if you have it in a little jar, I could touch this to the outside of the jar and it will attract the magnet. So theoretically, as we have this lava lamp going, we are going to be able to connect these little things to it to drag them around. And it seems very fun. Now, Stick here mentioned that he is going in a palindrome rabbit hole right now, along with some other things. Like I mentioned in the last stream, I have been looking at palindromes myself too. long ago, I really did a lot of research about palindromic numbers, and I made an episode that I really like about those on the Combo Class channel. So that's one of those things that's not talked about enough. It's rare enough that I hope that, I mean, I'm not glad it's rare to discuss palindromic numbers, but the one benefit of that is that if some teacher Googles palindromic numbers, my video could come up because there's not that many resources on it. Now, apart from the palindromic numbers, what I've been looking at is palindromic sequences of sorts, because when I did recently that square number thing, and for those who looked for some clues in my modular exponentiation thing, you may have noticed it worked for not just squares, but for even powers, fourth powers and sixth powers too, was that they generate palindromic strings of what the last digit will be if you look in a given base. Now, okay, this does really look like a beverage that you would drink, so good thing they wrote on top, don't open, don't drink. Good warning. You know what this warning reminds me of? So, I'm in the car driving on a very busy street where in a car, this is today, when I was coming back from the mailbox actually, on a very busy street where you can't be super far from the car in front of you. It's busy enough that you got to be pretty close car to car. And look at the warning I saw on the truck in front of me. I took a little photo of it because I thought it was funny. So this truck right in front, this is just kind of big, but not that weird looking for a big, like, the type of truck that carries stuff, you know, big, something for some company or whatever. They had this warning on the back that says, warning, stay back 200 feet. Not responsible for broken windshields. It's like, what are you talking? How am I supposed to just stay back 200 feet? There's no way on the street they were on that you could have stayed back 200 feet. And you probably couldn't even read the sign from 200 feet away. So what's the goal? That you then read it and then back up really quick? But yeah, someone said they wouldn't have even read it. Do you mean you would have just drank the liquid right here? Yeah, they probably had somebody do, or they either had somebody do that and sue them, or they were worried that was going to happen. You know, normally you'd say, logic would tell you don't open and drink this, but don't, you know, open and drink a beverage that you don't know what it is. But nowadays, someone would be dumb enough to drink it and then greedy enough to sue the company. So can't blame them for putting the don't open, don't drink label on it. And somebody says, Happy Teacher Appreciation Week. That's cool. Yeah, I do feel like a different sort of teacher, but a teacher nonetheless. It was only a few months ago that I was actually a private teacher in music and math lessons. But a month or two ago, I decided to dedicate all my time to combo class and be this sort of teacher instead. Now, there's going to be another week. So for this week, don't only appreciate me, but appreciate some of your favorite teachers. Now, if you told your if you go to school and you told your teacher a compliment about anything about that you like about how they've taught you something, that will make their week probably, because you know that teachers don't get a ton of compliments from students. So I mean, I do. I get a ton of nice comments, but I mean like teachers in school. So another week this year, I'm going to make it be called Tell Your Teacher About Combo Class Day, because I think combo class should be played in more schools. Not necessarily this channel as much. This channel is a little freeform, but my main episodes. Now, let's see how we're supposed to plug this in, because I do keep getting distracted, and if it's going to take up to an hour to heat up, then we should get that going. So it says, first time use, the first time you turn on the display, there may be a density gradient in the ferrofluid. This will most likely cause some ferrofluid to rise to the top and not return to the bottom the first time it operates. On first use, you must allow the display to warm up long enough for the ferrofluid at the top to remain liquid about 1 hour, then use the magnets to mix the top and bottom ferrofluid together. Grab as much ferrofluid as you can from the bottom and bring it to the top with the rest of the ferrofluid to create one blob, then move it around and play with it until the entire blob sinks when you pull the magnets away. Cool. You know it's a good product when they have an instruction that is a warning for your first time use, but the instructions of it involve the words, play with it. So, good product alert so far that they're telling me very formally a correct way to play with it the first time. Then, you know, they leave it up to me how I'm going to play with it the second time. And they say, think of this as calibration. If you do it right the first time, you won't have to do it again in the future. All right, so the ferrofluid is solid at room temperature. It's at the bottom right there. It's the stuff that... So basically, anyone who drinks this would probably... If you know how you're not supposed to drink it, but if you did, what it looks like to me is if you had some melted, like, boba, those pearls, tapioca things, like a few of those, but like melted in a blob at the bottom, and then a bunch of water on top. So it says it's solid at room temperature. Once the lamp's on for 30 to 60 minutes, it'll start flowing. Okay, and it says, do not leave magnets stationary against glass for long periods of time. This causes permanent stains. Cool. Wait, what? Oh, wait a minute. So, I liked these instructions at first, but this is confusing me a bit. The very top starts with an unpacking instruction, and they told me, you know, just how to unpack it, which I did correctly, luckily. And then it says assembly, and it starts with number 37. What? Where's numbers 1 through 36? Why are they starting at 37? You see that? Okay, we're going to assume that they meant 1, 2, and 3, and by some strange combination of typos, 1 became 37, 2 became 38, and 3, which is the least weird of the typos, 3 became 39. Okay, and well, the assembly's really basic. They could have even made these one direction. The first 37 is to screw the bulb in the socket. 38 is to place the bottle in base. And 39 is to place the cap on the bottle. Wait. Place the cap on the bottle. Isn't this the cap? What do they mean place cap on top of bottle? Was this cap not supposed to have been on there before? Okay, we'll figure it out. Ew. This is the cap. The cap is so that it makes the top look more pretty and you don't have to read the don't open, don't drink thing. It covers that up so that if you are dumb enough to drink it, first you're like, aw man, when you see the warning inside. So, yeah, it is funny about the unpacking directions is like 10 times as many words as the assembly directions. Unless I'm missing steps 1 through 36 for real. So, we're supposed to screw the bulb in the socket. screw the bulb in the socket. Here it is. A little bulb. So, we're going to screw this inside of this. It's hard. How am I supposed to get it in there? My hand doesn't fit in here. I'm going to like drop it in really gently. It's hard. It's like not hand sized. Okay. So, to whoever said it looks like a lava lamp, it does. But normally lava lamps, I don't know what they're made of. Let's see what lava lamps normally have in them. What's in lava lamp? Lava lamps normally have paraffin wax. Now, normally it flows around in there because of the heat or something along those lines. But now we are going to have more control over it because ferrofluid will attract to the sides when we touch it with these. It's going to be maybe reminiscent of this plasma orb here where you... Oh, okay. As I moved the plasma orb, the toroflux expanded. But of the plasma orb here, when you touch it, it does stuff. And so will this. Now, let's get this plugged in so that we can move on to some other topics and let it charge. All I need to do is screw the bulb in, place bottle in base, and then I guess turn it on. So, we have to, I'm just going to set it to the side. I'll move the camera to it if it does something cool, but I'm just going to let it chill over there for a bit because I want it to properly warm up. Okay, I do have to be careful about knocking this over because the bulb screws in. This does not screw in, it just kind of sits in. So, I'm going to have to put it somewhere flattish. All right. One moment. And in the meantime, we can look at the toroflux. We'll get this plugged in and then begin a little mathematical topic while we wait. Now, our mathematical topic... Alright, I think I've turned it on. A light went on in it. Okay, yeah, a little light went on in it, so I think it's hopefully heating up. So, if anyone wants me to check on it at some point, leave ferrofluid in a comment to remind me. We are going to now take a break from that and get into some other discussions. Yep, as soon as I plug in the computer too, so that we don't have to deal with that later. Okay. Now, let's actually, okay, we'll read about ferrofluid when we go back to check on it. We'll go back to a math topic first. Once I make, okay, these will just be intertwined for a minute. So, what I would like to first talk about, although feel free to keep leaving whatever in the chat, I will check that periodically. What I would like to first discuss is, actually, where did the chat go for me? I need the chat back. Okay, so sometimes the chat goes away just from my end, so I'm going to need to pull it up and make sure that I do not play an ad. I'm pretty sure I have the sound off. We're not going to hit that curse again. So, what we're going to discuss today is okay, sorry, just one second. I gotta get this there. Okay, now I have my chat for sure. What we're going to discuss today is the number 125,000. It could be fun to discuss a number that we just passed in subscribers and call it a subscriber special for fun. But 125,000 is a particularly notable one. I don't just mean because it's an increment of 25,000 that seems like, little chunks in our base 10 system. I wouldn't do one for 175,000. 125,000 is different. Now, there's two reasons 125,000 is cooler, and they sound different, but they're actually very linked. One reason is that it's a perfect cube. It is 50 cubed. The other reason is that it is a unit fraction of 1 million. It is 1/8 of 1 million. Now, before I go into this in a minute, think for yourself, why are those facts actually the same? The fact that it is 1/8 of a million and the fact that it is 50 cubed. Well, the way I described it in the title, by the way, was I figured if you're going to say some amount of m's are millions, then you could say 1/8 m is 125,000. And so in normal math terms, we can call that m over 8. Now, it sounds weird to just put m on top without a number, but it kind of works. It's million subscribers. So maybe m implies 1 when there's no other number. So we're calling it that we are at m over 8. Now, that's pretty wild because this channel's like 8 months old, so or almost 9 months old now. Not even, no, it's closer to 8 months old. That is crazy. Super cool. So not only is that awesome, but the number is pretty neat because what I want to show real quick is some lists of different okay, I'm going to pull open the OEIS so we can see these lists for real, that you can see them with me. And the OEIS, as many of you have seen on here before or may already know, is called the Online Encyclopedia of Integer Sequences. And let's say I want to know a list of what other numbers are in the family, not just cubes, because then it's sort of like, why are we only giving credit to cubes and not the other powers? What other numbers, like 125,000, are a perfect power? Starting with that, which includes all the squares, cubes, and fourth powers. Perfect power just could be any a to the b with b 2 or more, and their whole numbers. Now, if I want to know that, I could search the first few that I can calculate in my head. I know that the first few are 1, 4, 8, 9, and there we go. Perfect powers. Oh, I need to show it to the screen here. So, there we go. All I did was search 1, 4, 8, 9, and it brought this up. Perfect powers. They also will have a longer list here, typically. Table of 1 to 10,000. And if I go to our range to see how many are perfect powers around the number we were talking about, 125,000, we could see there's kind of a lot. And that's mostly from the squares. Most of these are going to be squares. Now, here we could see, for example, we've probably already passed the next perfect power. We're probably already past 125,316. So what if we wanted to say, well, it's a little rarer than just all these perfect powers that include squares. Maybe I want to know what other numbers are a little rarer like this one, in that they're a perfect power, but the exponent is bigger than 2. Now, that's actually a little different than if I say the non-square perfect powers. The reason is because fourth powers are also the square of something else, so any even power is also a square of something. And so if we say the non-square ones, that's the most restrictive of those. Well, most restrictive would be to say just cubes. But, you know, to widen the gates a bit, we'll start with one restriction at a time and first say, what if I want to know, not kick out every square, but they need to have a power more than 2. They have to be more than a square at least. And so I could search the first few. 1 will probably still count, because as long as you let 1 be one of your base numbers, 1 to any power will work. Now, after that, we're not going to do 4, but we'll do 8, because 8 is a cube. Next, we are not going to do 9, but we would include 16. So let's see if that brings it up yet. Not quite yet. We need another term or two. Well, I mean, it might be like the second sequence or something. But let's pull up 1 or 2 more terms. The next perfect power that's more than a square would be 32. And then you'd have, let's see if that brings it up. Not yet. So let's see. There's a chance they didn't include 1. So let's cut that off and add something else after. We have 8, then 16, then 32. Then I guess it would be the next cubes, because the next 5th powers would be too big. So our next cube would be 125. Maybe I'm doing one of these terms off here. Let me see how we could find that. So I think if we go to the other one, they have one. I partially have the clue. I don't know this will pull it up necessarily, but I think I remember seeing before that they do have it, and it might be called a similar thing with that as 3. Okay, 3. Let's see. I swear I found this at some point. That's okay. We'll try and jump to non-square perfect powers. So what we would have looked at there, which I might have gotten, you know, missed one of them or something, might have been why that was, oh yeah, maybe it was 2 to the 7th power. Would that be in there first? 2, 4, 6, 8, 16, 32, 64, 128. Not quite. What sequences is 125 then 128 on? Because that's on the general perfect powers sequence. One called powerful numbers. And a variety. If anyone finds what I'm talking about, leave in the chat. The OEIS, where it's perfect powers, but K is at least 3. I'm pretty sure they have one of those. But what we'll look for here is if we can search up non-square perfect powers. And this is the more restrictive of those. Now, if we say non-square, they can't be 4th powers, 6th powers, 8th powers, or any of that. They have to be something to an odd power. And they can't be anything to an odd power, because it can't be like a square number to an odd power. Otherwise, well, actually, let's see. A square number to an odd power. Yeah, let's see our longer list. And we can see that early we have 2 cubed. Then we have 3 cubed. Then 2 to the 5th power. Then 5 cubed. Then 2 to the 7th power. Then, let me make this a little bigger. Oh no, not settings. I wanted to make it bigger. Maybe that's not how I do it. I'm on a new computer and not a tech wizard. So, here we got 3 to the 5th power, I guess. Is that right? No. Is that 3, 9, 27, 81? No, that'd be 243, I believe. So, non-square perfect powers. This would be 6 cubed. So, now, let's go to where we are and see what they're where, and then we'll look at the whole pattern. So, since 100,000, there's not nearly as many of these once you've kicked the squares out. The last one was 110,592. Then it goes to 131,072. This one I'm pretty sure is a power of 2. Not positive. This one I don't know what it is. This one, though, is easier to figure out because of all those zeros at the end. What really is making up the number that we're talking about, 125,000? And what if we asked a particular question? What if we asked, well, this is what you can call a round number in our base, in that it ends in multiple zeros, sometimes nicknamed a round number. And it's also a perfect power. What other numbers would be similar to this? What other numbers would have just a few non-zero digits and then say 3 zeros after, like this one had? Well, let's start with, what does it mean to have a 0 / what does it mean to be a perfect power? What does it mean to have a 0? Means you have a 2 and a 5, each as a prime factor. So for each of these zeros, we have a 2 and a 5 in the mix. Now, let's write this on the whiteboard if I have a working marker. And it's got to be around here somewhere. Let's see if this works. No. Oh. Okay. Here's one that kind of works. Here. If we look at 125,000. Now, what we're on the road to find is, why is it m over 8? Meaning 1/8 of a million. Why is that related to the fact that it's 50 cubed? And what other perfect powers are round numbers in our base like that? So, what we'll look at first is what makes this up so far in the 0 parts is 2 cubed, because there's a 2 as a prime factor each 0 contributes, times 5 would be cubed. We would have 5 cubed. However, this 125 part is 5 cubed. So we have 5 to the 6th power, because we got 3 5s from that and 3 5s from that. So this looks like, okay, we have these guys up to high exponents. That's on a good track to be a perfect power. But here's the thing. If I looked for, say, 121,000, that would be 2 cubed times 11 squared. It's square, times 5 cubed. And that's not a perfect power. Now, even if I looked at something that was just 2s and 5s like that, if I don't get it just right, if it's Say, for example, I have 250,000. Well, now this has 4 2s in the mix. And, well, no, wait, this would work. Let's just say it's 25,000. 250,000 would be a perfect power. 25,000, let's say. That's similar to our 125,000. That is 5 to the 2 there and 3 there, so to the 5th power times 2 cubed. That is not a perfect power. So, what's different about these? Why is 125,000 a perfect power and 25,000's not? They both have these loaded up exponents. Like, if you first saw the difference, you might think, like, is it that we need something as high as the 6th power and that was only to the 5th power? But we don't. We can make perfect powers that are smaller. In fact, 25 without those zeros is a perfect power. In fact, 2500 is a perfect power, which is 5 to the 4 and 2 to the 2. 2,500 is a perfect power. Now, I don't know these from making up some list. The way I know these is because these are easy enough numbers to prime factorize. And so I was able to bust them down to prime factors, and that secretly is the code. Now, some of you may remember a clue I gave in an episode I made on the Combo Class channel at one point about what's called prime signatures, where we saw that these things called prime signatures are a way of telling what a bunch of types of number are. And one of the things they had a classification for was perfect powers. Now let's start with the fact that this one's a cube. Cube is an exponent of 3 up there. 125,000 is 50 cubed. And here in the prime factorization, they're not both 3. However, they are both 3 Vin. Not the base numbers, but the exponents. So, is that a clue that this was 3 and these were both 3 Vin? Multiples of 3? It is. It turns out, and for those who didn't see the prime factor or prime signature thing, what that was about is we can just take out the exponents numbers and ignore the base numbers and get a surprising amount of data about the number, such as if it's a perfect power. If I only knew that a number was in the form a to the 3 times b to the 6, with a and b being different positive integers, are different positive integers greater than 1 for both of them, then I would know it's a perfect power. And if that was a to the 3 times b to the 5, I would know it wasn't. That's how powerful these prime signatures are. Sometimes you can ignore part of the thing and get a shocking amount of data from the other part. In this case, we have 3, 6 as the exponents. In this case, we have 2, 4, because we can write them just in ascending order, regardless of how I wrote those. Now, 3, 6 here, we said was both 3 Vin, and it is actually true that if and only if your prime signature has elements that are all 3 Vin, meaning the exponents of the prime factorization were all 3 Vin, then it's a cube number. A similar thing happens for squares. This one is a square, and it would be 50 squared. So that is 50 squared, actually. Kind of like that's 50 cubed. It's kind of coincidental that that worked out. It was because I tried to make it work. I had to shave off a 0 or 2 to make it work. And by the time I shaved off a 0 or 2 and kept it trying to look similar in a way, it ended up just being the square version of the cube. Now, with this one, they're even. Both of them are even. And that makes it a square. If there were multiples of 4 for every exponent, power of 4. And etc. Now, that even explains why all powers of 4 are squares. Because it's like, well, if they're all multiples of 4 in the factor, in the signature, they're all multiples of 2 also. Now, how do we describe what that means for perfect powers in general? We can say that if your prime signature has all of its elements there's a few ways of putting this. One way of putting it is have a factor in common that they all share that's larger than 1. Another way of putting it is to say the greatest common denominator. And there's other ways we could factorize it. And, I mean, we could say what's going on with the factorization. But essentially, the easiest way to think about it is that if they all have some factor in common more than 1, that factor is an exponent on like if there's some representation of the original number that is some whole number to that exponent of whatever the factor in common was. So let's whip up another example. Let's say, just to like make sure it sinks in for everyone, let's say I encounter a number that ends up that I was like, is that a squirrel? Because I saw it in here, but no, I'm just bumping that. So let's say we find a number that is 2 to the well, let's say we have I'm going to do a number that's bigger than we actually are going to write the number, because this would be really big, but I just want to give an example. If I have a number that factorizes as 2 to the 12th power times 3 squared times 5 cubed. Well, no, let's say 3 to the 6th power times 5 cubed. Well, the biggest factor they have in common is 3, so the original number is a cube number. It's not a square number because this doesn't have a 2 in it. If, say, this had been a 6, or let's say this was 18, 5 to the 18th power, now it would be the 6. Let's say that these were all really big ones. Let's say it was 12, 18, and 24. Well, yeah. Now it's not just the smallest one of them, is what an example I wanted to give too. In this case, we have to look at what's the biggest factor they have in common. That would be 6. So this would be a 6th power, which is a square and a cube. So this is a square, cube, and 6th power, that original number. But it is... And it's also a 4th... Wait, it's not a 4th power, because 18's not divisible by 4. So, that makes it pretty simple to know. So, how does that help us if we want to know which perfect powers are round numbers with a certain amount of zeros? Well, the certain amount of zeros is going to be a 2 to some power and a 5 to some power. So we're going to have to make sure that whatever the rest of the number is, apart from any 2's or 5's that might add to the 2's and 5's, is after it's added any more 2's and 5's, that all the non-2 and non-5 components of it are a multiple of what the 2's and 5's amount was. So let's see an example. What if I add 900? This is 30 squared, and I know it's a square number because this part of it is 3 to the 2nd power. This part of it is 2 to the 2nd power times 5 to the 2nd power. And these all have a 2 in common. So that is a square number. Now, what if we look at 9,000? Then it would have been 2 to the third power and 5 to the third power, 3 to the second power. The exponents don't have a factor greater than 1 in common, not a perfect power. So, we were looking at one that had 3 zeros at the end. If we had something that had 3 zeros at the end and something in front, what we have there is 2 to the third power and 5 to the third power. Now, if this thing contributes a 2 and a 5, we're going to get another 0, and it wouldn't have just been 3 zeros. And we said we're looking at ones with 3 for a moment. So, if this thing contributes one of them, though, if it contributes either a 2 or a 5, which is possible without getting another 0, it would have to contribute 3 of them. Otherwise, we're going to lose that 3 in common with the multiple. Like if this right here, it has this little chunk, has 1, 2 in its prime factorization, that's going to make this 2 to the fourth power times 5 to the third power. Hard to get a multiple in common out of that. And so, or a factor in common. So, one way we could nudge them all the way up is by adding 3 to one of them. One option would be if we add 3 2s in the mix, we get 8,000. 8,000 is a perfect power. It is the cube of, it would be 20 cubed. And the other way would be we could add 3 5s in the mix, and that number is 125,000. So, that was a way we could calculate it. Let's think. What other ones would there be? Well, we could also have a different prime to the third power. And if that's small enough, the prime to the third power, we could try multiplying it by 8, because that would add just 3 2s in the mix. Or we could try multiplying it by 125, but that's going to get pretty big. So, what other primes could we throw in? We could do 3 cubed is 27. 27,000 would be 30 cubed. Perfect power. Now, what else could we do? What about 27 times 8? Whatever 27 times 8 is, which would be 216, I think. 216,000, I think, would be, which we saw in the list a minute ago. We said that was 216 on its own was 6 cubed. And we can notice that because here we have 3 to the third power. Well, this would go up to a 6 there, because 3... we have 3 2s paired up with that to make this part of it, and 3 more 2s paired up with the 5s to make that part of it. So, the ones that have 3 zeros at the end, and, 1 digit before that and are a perfect power, would only be 8,000, because that's the only cube of something there that could match those 3s. And if we have 2 digits, we could go for 27,000. 3 digits, we can go for 125,000, and then, our options start expanding too, like 216,000, things like that. So, we can see 216,000 on the list here. Now that I look again, we saw 216 before. And, yep, 216,000 is on there. So good comparison of this could be, which ones of these show up later? Because these, we said, were non-square perfect powers. That means that it's a good chance to fit along with that 000 thing. 8,000, yes. 27,000, yes. And 800, no. 2,700, no. 32,000, no, because that is 2 to the 5th power. So look, no 32,000. So, I hope you like those techniques. I will, as usual, have a clarification of that at some point in an episode, but we already went into to a degree, the prime thing in an episode called something prime signatures. So if you look up combo class prime signatures sometime. Now, what we will also make a bonus video clarifying sometime is that other part, which is quick techniques if we randomly ask the question, which perfect powers are round numbers? Because we kind of only looked at a corner of it by asking, I simplified it to which ones end in 3 zeros for a minute. The ones that end in 2 zeros would, have their own version of that. So the next perfect power we're going to hit is 130. That's not a square, is 131,072. Now, let's see. Ooh, the ferrofluid's doing something kind of cool. I'll show that to you in a minute. It's starting to crawl upward a little bit. So, now, the other thing I wanted to note, though, in the math section is that I said that this somehow ties into the fact that it's 1/8 of a million. So, well, we saw why it makes sense for it to be 50 cubed, because, of the 50, the 5 part at the beginning made that, and the 0 part at the end made that, basically. But why is it 1,000,000/8? Well, here's where the problem-solving mind would want to go. It would want to think, well, 8 doesn't really seem like it has that much in common with 5 cubed, except for it does have 2 major things in common, which is that 8, if we look at its prime factorization, is 2 cubed. So not only is it also a cube on the denominator, and we were saying something about cubes going on, but it's paired up with a 2, and we were talking about how 2s and 5s get paired up a lot. So what's going on here is that to turn this 125,000, which was 2 cubed and 5 to the 6th, into 1,000,000, what we have to do is make it 2 to the 6 times 5 to the 6. That gives us 6 zeros. And so when we're saying it's 1/8 of a million, what we're really saying is, it would have 6 zeros, but it's missing 3 of the 2's in the prime factorization. So what would be, something with 6 zeros missing 3 of the 2's? 2 to the 3rd power times 5 to the 6th power, this thing. But here's another thing I want you to ponder, which I will turn into an episode at some point. How can you connect this all to the fact that 1/8 in decimal is 0.125? So it looks like 5 cubed with a point in front of it. Now, in fact, 1/4 looks like 5 squared with a point in front of it, and 1/2 looks like 5 with a point in front of it. So I will, make an episode about that at some point. For now, you can think about your own logic, and for those, if you ever encounter a question from me that you already know how to solve the answer, a secondary question to try and crack is always, to what degree can I justify or prove this answer? So, hope you all enjoyed that. I am going to take a little peek at the comments. So, somebody asked if I've counted my clocks. Well, actually, let's see. Okay, I will do comments first. I said normally on Mondays we will do our intermission at 5:55, so people know I'm back at 6 at my time. But we'll do it a minute or two late. I'll answer a question or two first. Someone asked, have I counted my clocks? Not super recently, but at some point I have. I believe we have somewhere around 40, although some are small and some are broken, so some would maybe classify it as 30. Somewhere around there, and some of them are quite large. Now, Somebody said pi, Euler's number, or the golden ratio. Which one do I sacrifice? Oh, that's too hard of a question because I love all of those dearly. I honestly don't know if I can pick. The thing is, a lot of people, or a lot of mathematicians at least, would probably sacrifice the golden ratio because pi and Euler's number show up in so many contexts and are really fundamental. Not that the golden ratio is not, but also pi and Euler's number sort of seem more mysterious to some because they don't have they're not algebraic. They're called transcendental because you can't write them just with like square rooty things like the golden ratio. But the golden ratio is in some ways the hardest to approximate with fractions, a rational number. It's also in a way the simplest continued fraction of a rational number. I also have some very fond personal memories about it. So I kind of have to put it on the level of pi and d. Can't pick one, I'm sorry. Now, thank you to all the people comparing me to really historic great mathematicians. Somebody said if I was using base 6, how many subscribers would that be? Good question. Well, in base 6, that number 216 would be prominent. 216,000 wouldn't, but 216, we said, was... I mean, all these are still perfect powers in that base, but we noted that it was 6 cubed. That means 216 would look like 1,000 in base 6. So it would look like 1000. This one would look like that one if it was in base 6. But, you know, what we could do is look up a large power of 6. Give me 1 second. Let me pull open a good calculator. And we can figure it out, you know, just with sort of almost brute force by saying, like, what's 6 to the 5th power? That is lower than the number we're at. What's 6 to the 6th power? We're going to need to go higher than this. That is lower. What is 6 to the 7th power? This one, well, now we can multiply in our head that 6 times this would be too big, would be bigger than our number. So it's going to have a 6 to the 6th power as something there. In base 6, we can use multiple of them. So we would want 2 or maybe 3 of those. Is 3 of them too much? 3 of them's too much. We'd want 2 of that place. So basically we would just add on 6 to the 5th powers and 6 to the 4th powers and stuff till we got there. Somebody else can calculate it, what it would be in base 6. Leave it in the chat if you'd like. I already have done a lot of editing today about different bases. Make sure, if you haven't seen it yet, that after the stream you do watch the new combo class episode on that channel. It is linked in the description, and it is about fun bases. And to everybody who's complaining about their worries or fears about certain mishaps that happen in the episode, just know no functional technology was harmed in the making of it. So that was a few facts about the cool amount we're at. Even more important to me in a way is where the combo class channel is at, that one, and it hit a notable number too. It just passed 30,000, which is not a perfect power, but if we just look at the 30 part of it, because they match it up with K's and stuff, 30 is a very divisible special number. It's also a primorial, a product of the first some amount of primes by being 2 times 3 times 5. And there's actually a friend to it that I believe we also have passed at this point on the combo class channel. And let me confirm this one. Well, let me just get that calculator back. and here's what I pulled up is the prime factorization of another kind of random looking but cool looking number, 30,030. Now, it might just be like, well, that number probably just looks cool in our base. Maybe a coincidence that it looks like all that stuff. It is a sort of coincidence that it looks cool in our base because it is a fundamental number. It is what we can call 13 primorial. Technically also 14, 15, and 16 primorial because those multiply all the primes up to that number and there are no new primes up to those points. And we can see that because this one is, look, 6 distinct. Remember in math is an important term. Distinct typically means they can't be copies of each other. So, because if you just say different, it can be a little ambiguous if you meant that they can't be copies or there are more than one, you know. Here we have distinct. There's only one copy of each. 2, 3, 5, 7, 11, 13. Like, for example, just to clarify the terms, this number, 125,000, we would say that has 2 distinct prime factors because there's only 2 that are, you know, different than each other. But if I asked how many different prime factors does it have, it's kind of ambiguous what I mean. So, 30,030 looks sort of cool because it has that 7 times 11 times 13. And 7 times 11 times 13 copies a 3-digit number. It's because 7 times 11 times 13 happens to be 1001. So if I multiply this by like 321, it's going to be 321, 321. If I multiply it by, 476, it's going to be 476, 476. And so when I multiplied that by the primes leading up to 7, 2, 3, and 5, well, those contributed 30. So it's going to be like I copied a 3-digit version of 30, which is 030. Is if I wrote 30 and they're like, write 3 digits, it would be like, okay, 030. And so that's what this did. It copied the 030 as the 3-digit part. So not only is this number a fun example of this 7, 11, 13 thing, but primorials are pretty cool. Primorials will come back. We will do probably a whole episode at some point dedicated to them. They have shown up in the way I constructed, in one of the first combo class episodes, how I constructed my version of a classic proof about that there are infinite prime numbers, and that can be done with a primorial's help to speed up the process. So that's pretty neat that both those channels are doing well. The new one on this channel that's doing well is the newest one about what digits can square numbers end in, which, as I expected, sometimes the bonus channel ones do, which is this channel, do better than the main channel ones even, because they're simpler titles for people to digest sometimes. People are like, oh, what digits can square numbers end in? I get that question, But I think the new one on the Combo Class channel is doing well, because I think people can get the question, the base some computers run on that's not binary, which is not in the form of a question, but you know what I mean. So, the ferrofluid is creeping up and maybe blobbing up as well. Let me show you a little peek of it. So, to those who are new here, we have this ferrofluid lamp that is a magnetic type of stuff that will be cooler than a normal lava lamp, and it needs a little while to heat up before we start putting magnets on it. And this is what it's doing right now. Can you see that? Let's see. So there's like this black stuff at the top with this demonic looking tail, and then there's this like even more demonic curl coming up. This stuff looks cursed in a cool way. All right. So We're going to take a real quick intermission. I'm going to run inside to grab some water and go to the bathroom. And then we will look up what ferrofluid is, chat about some more math, and then check out how the lamp's doing. Leave a comment about, let's see, what is your favorite non-square perfect power? Hello. Welcome back to my combo lords. Somebody says if they had a nickel for every time they wanted to have $125,000, they would have some good. They would have enough sense to buy Gumball. Maybe not in this economy. But yeah, it would be cool to have $125,000. We have 125,000 subscribers, which is almost in a way cooler to me. I'd probably pick that over $125,000 if I had to like lose my channels or have that. But it would also be cool to have that. Trust me, I run on a very low budget, but we make it work. Now, somebody's commenting about if any clocks are ticking. I don't think any are moving. They better not be, as sneaky fellas. If they are, I'll make sure they're not next time. Now, I was thinking about a lot of different ways we could make clocks better. I have a lot of upgrades for clocks, and I think, although this sounds a little absurdist, that if I ever sell any sort of merchandise for Combo Class, one of the first things I would want to sell is a better clock. All right. Now, someone said, as a general safety rule, not to put or store magnets near computers, data drives, or electronics in general to be safe, which is a good reminder, and I should probably keep them even a little further. So let me slide them even a little further from the electronics. And that is smart. You don't want to wipe out a hard drive or anything. Now, somebody's asking how the golden ratio relates to the pyramids and planet Earth. Now, I have kind of bad news. The good news is that this does not mean that the golden ratio is overrated or anything. The golden ratio is unbelievably cool in math. However, it's a little overrated of how it's described in terms of things like pyramids, things like old architecture. A lot of those things are going off the golden spiral, which is really one tiny aspect of the golden ratio. A lot of people think it's about this spiral thing. That is one visualization of the number. That's a really small component of what it can do. And there's a lot of things that have sort of like taken an old classic painting or something and been like, look, it's kind of in that shape. It's making a spiral. That means it's the golden ratio. And not only is it like pretty easy to line that up on that scale and make it just like look correct for most paintings and stuff, but there's a lot of spirals in nature. There's logarithmic spirals and other things. And so like seashells and stuff, some might have the golden ratio, but if you see a spiral, it's not like, there's the golden ratio. So a lot of that stuff of how it shows up in nature and in stuff like that is a little overrated, or like, I don't know what the word is for, you know, overly considered true when it's only mildly true. But that doesn't mean it's not in nature. It does show up. The thing it shows up the most in nature are certain flowers and things make their petals in Fibonacci sequence like patterns, and those relate to the golden ratio. So there are certain times the Fibonacci sequence shows up. Additionally, that can show up, the golden ratio, sometimes from the Fibonacci sequence, can show up in growth rates of things. The amount of animals in a colony over time can relate to that sometimes, among other things. And so I am going to have to make a video someday about, is the golden ratio overrated or underrated? And part of the thesis is going to be that it's kind of both, because it's a little overrated in how it is played up in nature. But if anything, it's underrated in how many cool mathematical traits it has. I have a whole book about its mathematical traits, like, that I bought a long time ago when I was young, one of the first math books I bought. And someone said their favorite perfect power is 27. Now, someone's noting it shows up in the bulbs of the Mandelbrot set. That's quite cool. The Mandelbrot will also need its own episode sometime. Very cool. Now, leave more comments if you have any thoughts. What we're going to do for a moment is look up Ferrofluid, and then we'll see if it's been an hour, and then see if we're supposed to use the magnets on the Ferrofluid in some way the instructions said. So, let's see. I am large, so I'll shrink myself. And we'll go to the Wikipedia I have pulled open for Ferrofluid, because like I said, I am not an expert in this stuff. This was a cool gift from George Carozzi here to my mailbox, which the address is in the description. If anyone has any old clocks and dice and stuff they need to send. Now, let's see what we can read about this, since I don't know too much about it yet. It's a liquid that is attracted to the poles of a magnet. It's made of nanoscale ferromagnetic, which is magnetic properties that maybe not necessarily made of a typical metal you'd expect. What is in it? Nanoscale particles of magnetite is a mineral, hematite, and some other compound containing iron, and a liquid, usually oil. So it wasn't water in the do not drink thing, it was oil. And ferrofluid, and these things. No wonder they said do not drink. I don't think they're putting magnetite in the daily vitamins. So, a lot of interesting facts we won't go too deep into. Essentially, with ferrofluid, the reason they're showing these weird, almost spiky looking shapes is that if it's flat and we put a magnet near it, it'll spike up to try and go close to the magnet. Now, magnetism is a really important force. Magnetism is a big one, because, like, a lot of other forces can be explained in terms of, like, gravity and other physics things. And magnetism is its own force that is, an important aspect of how whole planets are formed and such. I mean, not necessarily how they're formed, I would have to look into that. But what makes the universe in its current state definitely relates to magnetism. So, future applications, maybe it'll show up in spacecraft propulsion or medical fields or energy harvesting. So, I think it's been almost an hour. It's probably been at least an hour. So in a minute, I think we'll actually get the ferrofluid thing closer over here, try out whatever the instructions say we have to do for the first time to make sure it's calibrated. So, someone's asking, is a magnet a ferrosolid? And I am not sure how you'd describe it. It is, I think the ferro refers to a particular thing about it, because they call it ferromagnetic, not just magnetism. It says, yeah, ferromagnetic materials are familiar metals that are noticeably attracted to a magnet. So, yeah, leave a comment if you know any more ferrofluid facts. Not positive about all the details, but I'm going to bring over the lamp. It can't, or actually maybe I need to bring the laptop over there, because it doesn't have too much distance. I think I'm just going to need to, or no, I can move the power strip. It's in a power strip. We can get it over here. So, uh-oh. Okay. It fell a bit, and now it's probably really hot. It didn't break or anything, I just have to get it back in without it being too hot or anything. Okay. Hopefully that was inclusive in their steps about getting it all shaken up or whatever. Okay, let's see what's going on here. Now, that did shake it up, but it went to the top like they said. They said it's going to be on the top until we fiddle with those magnets a minute. Alright, now, let's get a better view. Gotta move stop school crossing sign. Now, over here, you see, we've got this strange black-looking stuff up on top. And we are at the angle where all you can see of combo class is the last 3 letters, which, you know, when we point the camera at the wrong way, the last 3 letters of combo class aren't the best position, but we'll roll with it. So, what they say now is, for the first time use, it'll be on top. Wait for the ferrofluid at the top to remain liquid, which it says about 1 hour. I can't tell if it's liquid. Some of it looks solidish, but that might be the bit at the bottom that got shaken up. I think it's liquidy enough. It's been an hour. Then use the magnets. I wonder if they mean the disc magnet, or these little magnets. I'll try the disc magnet, I guess. Use the magnets to mix the top and bottom. Okay, I already accidentally mixed it up a little bit when it fell off the thing. This top bit doesn't screw in, so we'll see. Are these going to be enough? Whoa, so look. I can drag it around, and they told me to mix the bottom ferrofluid and the top. We need to mix it all around. Grab as much as you can from the bottom and bring it to the top to create one blob, it says. Oh, that's wild. Okay, here, I'm just going to zoom in on the camera. It might get a little blurrier, but I'll just make us go, like, zoomed in a bit so that I don't want the computer too close to the magnet or the hot stuff or anything. So, we're trying to bring as much from the bottom to the top as possible. Maybe I should use the disc magnet. Yeah, this thing's way more powerful. Whoa, I accidentally got this whole ring up. I don't know if that's a problem. Okay, maybe the disc magnet's too powerful. What is the disc magnet for? You can place the magnets near the bottom of the base, but you don't want them close enough to magnetize it. Yeah, I don't know. Any ferrofluid experts know whether or when I'm supposed to use the stronger magnet or the weaker ones? I'm going to use the weaker ones now. The stronger one lifted up this whole disc thing from the bottom. Whoa, it looks all spiky. You see this spiky stuff? So, they said make one big blob. Join the blob. Okay. Is there any more down there? Oh, there are little bits. We'll get all these little bits up. Okay, I will use the disc magnet one more time. Oh no, it's getting this whole thing up, but we can get it back. The disc magnet attracts to the metal base of this, though. Okay. Now, what do we do now that we got as much as we can to the top? We move it around and play with it until the entire blob sinks when you pull the magnets away. All right, so gotta love how those instructions include play with it in their technical description. That is very... It might sound like I'm mocking that, but I'm not being sarcastic. I think that's a good instruction. All right, we're trying to move it around and play with it, but kind of tricky. Maybe I'll use the big magnet too. The problem is the big one attracts to the metal parts of this and to the other magnets. All right. Now, it says, if you place them on the base, don't make them close enough to the ferrofluid to magnetize it in any way. I guess that means just don't permanently leave them there. Because you're allowed to touch it, I assume, to the glass. Even though it kind of follows it even when I'm not touching it. Now, I guess I'll just fiddle this guy around for a while with this magnet and make it nice and blobby, like cook it up a bit. Until the entire blob sinks when I remove the magnet, they said. This is weird. It's like this weird blob of alien goo that's following wherever I want it to. Alright. The blob isn't sinking, so we'll just play around and stir it for a while I check if we got any comments and such. Cool. Not any harm, George is guessing, with any manual mechanical emulsification. And you can use the disc magnet on the coil at the bottom. That's cool. So, I assume I'm on the right track. Since you said you have one too, let me know if you recommend any other form of playing around with it other than sort of stirring it, which is what I'm doing right now. And it does feel like it's glooping up in a slightly blobbier way. It's like you're stirring some batter, or not quite batter, like you're mixing some paint or something. And somebody said combo class live with a question mark. And I guess maybe they haven't seen this channel as much as the other one maybe. But yes, on this channel, the Domotro channel, I go live every Monday currently, as well as one or two other random times each week usually. I enjoy going live, and people should know that they will always be a bit more casual than my full videos, but that they will still be quite fun and contain a lot of extra bonus learning and such. And in this one, we get an extra cool science experiment. Okay, so the blob is starting to sink a bit. Now, let's see. Do ferrofluids relate to the ancient pyramids because of pharaohs? That's a good one. I think that, yeah, the pharaohs probably have some fluids in the ancient pyramids, like some embalming fluid or whatever. And, yeah, someone's correct. Pharaoh does refer to iron due to ferrous, or Fe, for iron. So, I guess it would need an iron-based thing to be considered a ferrosolid. I wonder if you could call iron a ferrosolid. Maybe that's just like an anti-nickname because it's a lot longer of a term than you need. Okay, let's see what the blob does. It's sinking! So, most of the blob sunk. This little bit's still being on the wall. And there's actually a little bit on the ceiling now as well. Ooh, these bits want to go to the ceiling real bad. Alright, we'll let them go. And this bit is starting to just creep up in a strange coil. Whoa. You see that? Okay, let me get a good view on this again. Now we're really cooking. So, little bits of it are bulbing up. I'm not sure if you can see. And I can, like, let me coax that little bit out. I'm not even touching it right now. I'm like a centimeter or two away from the glass. Okay, that touched it. Whoa. Alright, now let's see what the little magnets can do. The little magnets, I can guide little clusters. Somebody told me to make a pancake in the chat. I'm not sure what shape you mean, apart from a shape like that sort of naturally forms, but there's a pancake. Now, let's make some other little shapes float off. Whoa, that one floated off on its own, that big blob. So, basically what it is on their own, it's going to have little bubbles go up at certain points and little bubbles go down, I assume, sort of like a lava lamp. And I'm not sure how exactly it decides when to go up or down. I'm guessing that when it's heavy enough, it doesn't want to float. So when there's enough in one blob, it sinks, or that part breaks off and sinks. And that if it's light enough, it might be able to want to go upward. But I'm not sure. I wonder if I could write something like this. I got myself like a 1 or an L or an I right there. That'd be a challenge. So, I think that is pretty cool. And yep, thank you all for the comments and such. We're not going to stream for a huge amount longer. My main goals of this stream were to chat about the number 125,000 and why it was one of our rarer round number perfect powers in the base. If you want something fun to think about, you could think about what would happen in other bases. Which numbers of that sort in other bases would something like 900 not have the zeros, or something like 216 have zeros. Like I said, that one would look like 1,000 in base 6. What other bases or what traits would occur in those, as far as the question I asked? Which perfect powers have a certain amount of zeros at the end? Ooh, that's cool. This blob went up, and then it, like, decided it didn't want to. It hit the ceiling, and it was like, nope, and went back down. Let's see if I can get it. Oh, yeah, it rejoined at the bottom. Ooh, yeah, I like this circular blob. Oh, and when you touch them in a certain way, they do get really spiky. Whoa, I'm not sure if you can see that. From the other side, it looks really spiky, the shape it makes. It's like this super spike thing. Let's see, this side might be better anyway. That side had some like packaging glue stuff on it that I'll wipe off later when it's not hot. This side we can see a little better. It looks sort of like a map right now. Anyway, we're not going to be doing it too much longer. But make sure that once I end the stream in a couple minutes, that if you haven't seen yet, you look at what's linked in the description, that new combo class episode, which I will discuss further in whatever next stream I do. I also still will be doing one that some people voted on the other stream, but then it didn't fit into last week because of the blackout stream and various lore. And that was a music-based one where I will make another beat using my semi-mathematical beat-making methods. And with those, I will have fun in a stream and show you that and explore the new computer's GarageBand, which is the simpler of this type of computer music-making software, that the simplicity will actually come in handy when teaching it or when showing examples to you folks, because it's easier to imagine what's going on and sometimes in a simpler program like that than in some program that you would, you know, use a bunch of settings on to make it sound really nice. Now, that will be coming at some point before long, and that'll be fun, as well as a variety of other cool bonus videos. But I'm extra excited about the main combo class episodes that I'm working on this month, including that one that just came out. Whoa, I don't know if you can see that. It looks like this spiky blob hanging on the other wall. Let me see to what degree you can see that. We'll get closer just for near the end and see how zoomed in we can get. So from this side, it looks more just like a black blob. But when you look at it from the side, it's really spiky. I don't know. You see that spiky quality in that thing right there? You have to look through it mostly right now. It might make it in the air if I agitate it in the right way, and then we'll be able to see it in the 3D fashion. So, ooh, a whole storm. Okay, so I think I read the instructions right. I think it was don't turn it on for more than an hour the first time. Always put the magnets on the base and drink this. No. Oh, no, those were the 3 things they said not to do. But no, there are other instructions actually that I should be careful about. It says, if the ferrofluid stays on top without falling, it's overheating, give it a rest, or plug in a dimmer switch. So that's something to be on the... Whoa! When you put up this magnet, a lot of ferrofluid sucks up from the bottom. It's like, I want to be on this magnet. This one gets like the whole thing on it. Pretty wild. Okay, so this will be a fun thing to put in the background of some of our less chaotic videos. Don't think I'll have this one on the desk if we do anything too wild. But, you know, in the videos we do that I don't expect many clocks to fall, that'll be nice to watch in the background. There's also this I should have put in the background of the stream. Quicksand painting. This will look nice in some backgrounds as well. And we'll see if after playing with the ferrofluid enough, it can take the throne of favorite new toy that I've gotten, but it's going to be hard to take the throne of favorite new toy compared to the Toro Flux, because no matter, I mean, the ferrofluid is probably the other coolest thing out of these things I've gotten so far. This thing I'm going to do a lot of experiments with. But it's going to be hard to beat how much I like the Toro Flux. If anyone can find me a large one of these, let me know, because when I looked online, I could not find a large one of these, for like a massive one, for sale. I was asking my friends about why it wouldn't be for sale, like I guess just not popular enough, or maybe they somehow trademarked the shape in certain ways. But at first one of my friends thought, maybe it's because you can't do the physics when it's that big and it only works when it's small, but I thought that doesn't make that much sense, I don't think. And then they thought maybe it's because it's too dangerous when it's big, because you see how it like springs open? Maybe if it was really big and it sprung open like that, it would like cut you. So I was like, maybe that's why. Maybe we'll have to try building the first massive Toro Flux. We're not going to be able to call it a Toro Flux because I think they have a trademark on that name. So we'll have to figure that part out. But let me know if you can find a massive one of these. Also, when I tried to look up giant plasma orbs, but the ones calling themselves huge are about twice as big as this. That's not what I call huge. That's bigger. That's an upgrade. I might still get one, but tell me if you actually find a huge one of these. And don't even contact me if it's less than 1/4 meter across. But yeah, I would love to get huge versions of these. That'd be pretty cool. Now, another fun thing that maybe we'll design is, I said we'll design this into a clock, which I do intend to do. I also realized one of these other toys I got, which is this foldy thingy that folds into different cubes and stuff. Well, I mean, no, it folds into one type of cube and also forms into other shapes. There are 2 that are not quite platonic solids, but similar to that, like fair dice shapes. One of which is a platonic solid, is you can make it into a cube. It's hard to, it took me a while to figure out the first time how you get the cube. But another of which is you can make it into a rhombic dodecahedron. And the rhombic dodecahedron, let me see if I can get it here, is a 12-sided shape, but a typical dodecahedron, here we go. The 12 sides are pentagons, but here they are rhombi or rhombuses. And although it's not in the Platonic solid family, because each of these is not a regular polygon, it is still a fair dice shape and one of the more elegant 3D shapes. And I realized, first I was thinking maybe I should draw numbers on these with like a white marker or something so that I can use it as a die, draw 12 numbers across. And then I thought, well, but that's going to spoil the cube. I wouldn't be able to put it on that and the cube, or could I? Well, the cube is an opposite face of it. The cube uses the other colors that are on the inside of the rhombic dodecahedron. And so I actually can. I'll be able to, in its cube shape, which let me try and find. I think I'm on the right track. In the cube version of it, I can, okay, here's a corner of what the cube would be like right there. I feel like it's close, but there's a face of the cube. And if you're wondering, this looks smaller than the rhombic dodecahedron, how could that be the same thing? It is a cube. The rhombic dodecahedron was sort of hollow. Now, I realized if I wrote dice numbers on the cube and on the rhombic dodecahedron, I could have 2 dice in one. It would still function as a toy as long as you didn't mind some half numbers showing up on certain things. So it would still, be playable. But if I figured out how to turn it into the cube or the rhombic dodecahedron quickly, it would be a cube that turned a 6-sided die that turns into a 12-sided die. So that I thought would be cool. Would be if I can make this, a rollable 6-sided die that flips into a rollable 12-sided die. Now, let's see. This is the second time somebody's asked about the clocks today, so we'll have to wait for another day about how many I have. Somebody says we could have a grandfather clock that runs on a swinging lava lamp between 2 magnets. Someone asked if they're allowed to say a dark joke. Trust me, I won't get offended. You don't say anything that's mean to a particular group of people or anything. So, if it's a joke that's like racist or sexist, you can skip it. But if it's just dark, then sure. I don't think I can get in trouble for 1 or 2 people saying crazy stuff in my chat. So, as long as it's not mean to any people, you can be a little crazier than I let myself be. When I'm with my friends, I make a lot of dark jokes. Maybe I'll make more dark jokes as the grades go on. Now, someone asked, will I do content unrelated to math someday? And probably. I have done content unrelated to math, but I'll probably do more. Originally, I planned on doing a big mix of science and language and math and stuff, and just got really carried away with liking the math the most, and it being what I was most knowledgeable about and stuff. And let's see. As far as content related to math of other types, there will be that, especially on this channel. This channel is like my playground, or I let myself do whatever I want on this channel. So this will have a variety of different types of things. The main things we'll probably be math, music, nature-related science, chemical experiment-related science, certain philosophical or historical things. Those are some things that we'll cover for sure. But I like all sorts of stuff. You never know. People grow and change. So don't get mad if I ever do weird experiments on this channel. It is sort of my bonus channel. If anyone ever thinks they're, bored of whatever I'm currently doing on this channel, just make sure you're at least tuned into the Convo Class channel. Now, somebody says we should include a sundial and hourglass into the grandfather clock creation. That does sound like a magnificent combo. In fact, that does make me wonder if I should try and combine those in some way to this clock or into some of the other things like that that are possibilities for making our own things around here. With the clock, I'm also thinking of how I'm going to phrase it, because I have some ideas of how to make a new type of numbering on the clocks. Now, let's see. I do think I am going to log off in a moment, but if people do have anything that they are curious in seeing that is non-math, you can always feel free to ask, and that might be even more likely than recommending a math thing that I would get to it or try it, at least in a stream or bonus video, because I have a huge list of math topics that anything already suggested will likely either be on my list or have to go after a really long list of topics I want to do about math topics. So if you have any suggestions for other stuff you'd like to see, you can let me know, because you never know, I will share other random topics as time goes on. We do snack breaks and stuff already. Now, I need to show my family this after the stream. They're going to think this is pretty cool, the Ferrofluid lava lamp. I'm going to go work on some random things now. Make sure to catch that new episode in the description. You can also catch me on the Patreon, subreddit, Discord, and places like that that are also linked in the description. And thank you all so much for joining me in this stream. And I will catch you in the next one. Or probably before the next, probably before the next stream, we'll have some sort of random bonus video. So I'll catch you in that. Thanks for joining me, and I hope you all have a great day.